Derivatives of inverse trigonometric functions. We start with the first derivative, finding dy by dx for y equals sine inverse of x. And here because we are dealing with sine inverse x, we will take at the beginning sine at both sides. Thus we will say sine y will equal x, and it is sine y equal x over 1. Okay? Now we differentiate both sides with respect to x. Thus the first derivative will be cosine y times y prime, implicit differentiation, equal 1. Then I'd like to isolate y prime alone, or the derivative y, by saying y prime or dy divided by dx equal 1 over cosine y. Now how to find cosine y? We need to go back to the fact that sine y equal x. We create a right angle triangle and we say, wait, sine y equal x over 1, and that would remind us of so. Thus it is O over H. Thus we decide somewhere in the triangle the angle y, and the opposite will be x, and the hypotenuse will be 1. Based on that, to find the cosine of y, we will apply the Pythagorean theorem to find the missing side, which will be square root of 1 minus x squared. This cosine y basically is radical 1 minus x squared divided by 1. If we flip it, we will have dy by dx. Since dy by dx for sine inverse x equal 1 divided by square root 1 minus x squared, if we put minus to this derivative, we will have d cosine inverse by dx. This part we're gonna find dy by dx for y equal tan inverse x. And again, we take tan at the beginning at both sides. Thus we end up having tan y equal x over 1. I'm gonna change the style of differentiating this time. I will say tan remind me of the word toa, and it is opposite divided by adjacent. Thus I will create now a right angle triangle where I have the angle y, and angle y has an opposite of the value x and adjacent of the value 1. Okay, now to proceed with what I'm doing, first of all, I want you to focus. Yeah, this is how I'm creating the right angle triangle, as you can see. Keep in mind, in this case, the hypotenuse will be square root of 1 plus x squared. I'm just applying the Pythagorean theorem here. Okay, now we have the right angle triangle ready. I will take tan y equal x, and I will do implicit differentiation. I will differentiate the whole thingy with reference to x. Thus I will say tan y prime, or the derivative, equal the x prime. That would be secant square y times y prime equal 1. Then I will isolate y prime. As you can see, y prime, or the derivative dy by dx, is going to be 1 divided by secant square y. I will remind myself that secant is basically 1 over cosine. Thus I will say, if I say 1 over secant, I'm saying it is basically cosine square of y. Thus y prime is basically the cosine square y, and it's gonna be 1 divided by radical 1 plus x squared. Thus you can see that y prime, or dy by dx, at the end will be, we keep in mind that we square it. Thus if we square it, the square root will vanish. Thus dy by dx will be actually 1 over 1 plus x squared without the square root, sorry. Now for y equal tan inverse x, if d by dx is 1 over 1 plus x squared, then guess what? D by dx for cotan inverse x is negative the value, negative 1 divided by 1 plus x squared. Now, if y equal secant inverse x, to find dy by dx, again we will take secant at both sides. The secant y will equal x, but we keep in mind that the secant is the reciprocal of the cosine. This cosine is a divided by h. The secant actually it is h divided by a. This h, the hypotenuse will be x and the adjacent will be 1. Thus now we're gonna create a right angle triangle with angle y. You can see that the adjacent value is 1 and the hypotenuse x. That gives you a clear idea that the opposite side, the missing side, if we are gonna use the Pythagorean theorem, it's gonna be square root x squared minus 1, as you can see in front of you. Okay, now we go back to secant y equal x and we will differentiate it, implicit differentiation, to find the value of y prime or dy by dx. This we will say, okay, the derivative of secant y equal the derivative of x, but you know that the derivative of secant y is basically secant y times tan y times y prime, this is an implicit differentiation, equal 1. Now we will isolate y prime by dividing by both sides by secant y tan y, and then we will go further with simplification, as you will see in the coming slide. Okay, now you can see, and I will keep in mind that the value of secant y, the value of tan y, that's from the right angle triangle TOA. Okay. Thus, as you can see, the answer will be 1 divided by x square root x squared minus 1. And as a tip, if d secant inverse x by dx is 1 divided by x square root x squared minus 1, if you put negative to this fraction, you will have d by dx for cosecant inverse x. Again, summary of the rules. When it comes to derivative of inverse of trigonometric functions, I want you to think about 1 plus x squared. I want you to think about x squared minus 1. And I want you to think about 1 minus a square. We keep in mind also the square root, like we have a square root 1 minus x squared and square root x squared minus 1. Now, as I said, when you are dealing with functions with letter C or letter T, you will have d by dx sine inverse x, it is 1 over square root 1 minus x squared. Now go to letter C, cosine. Put negative, cosine is attached, cosine inverse is attached with sine inverse. Thus it will gonna be negative 1 over radical 1 minus x squared. Now we go now to the third one, d by dx for tan inverse of x, which is 1 over 1 plus x squared. Now, cotan inverse is attached with tan inverse. Thus, we will say d by dx cotan inverse is negative 1 divided by 1 plus x squared. Now, the last one, d by dx secant inverse of x, which is 1 over x divided over 1 divided by x times square root x squared minus 1. All what you have to do to create the inverse, the derivative of cosecant inverse, just put negative for this value. Okay, just when you are dealing with inverse trigonometric functions, the derivatives, I want you to keep in mind this step in front of you. Now we will start with bunch of examples. Take the following example. Find d by dx for sine inverse 4x squared, and I want to focus at the chain rule in this stage. Now we need to keep in mind that the angle is, we will call it the inner, is 4x squared, and accordingly the differentiation of the angle will be 8x. Now to differentiate The inverse trigonometric function, we will say, okay, it is the inner derivative, which is 8x, times the rule of the derivative, which is 1 over square root 1 minus inner square. And you have to apply it like this, and that will be the final answer. Okay, another example. Find d by dx for cotangent inverse 3x plus 1. Now, the inner will be the angle 3x plus 1, and the derivative is going to be 3. Now, to find the inverse, the derivative of that inverse, we will say it is the derivative of the inner times the rule. Thus, it will be the derivative of the inner 3. And because you are dealing with cotangent, thus it will be negative 1 over 1 plus inner square. Thus, what is inner square? It is the angle. Thus, it is going to be negative 3 divided by 1 plus 3x plus 1 square. Now, we're going to move to the third example. And again, the inner is the angle x to the power 5. Thus, the derivative of the inner is going to be 5x to the power 4. Now, to find the derivative, we will say it is the inner prime times the rule. Thus, it's going to be, in this case, the inner prime, which is 5x to the power 4, times the rule of the secant inverse, which is 1 over absolute value of the inner, times the square root of inner square minus 1. But we already know what is the inner. The inner is the angle, which is x to the power 5. All what you have to do, just substitute, and if there is any chance of simplifying, go ahead. That was the end of the lesson. Thank you for watching.